Class, in this video we are going to start the topic triple product. So as far we have discussed the product of the two vectors. The one was the dot product in which we are going to receive a scalar one, and the second one was the cross product in which the resultant is always a vector quantity. But now we are going to talk about the triple products. Triple products is basically the product of the three vectors. So we are going to discuss that how are the or what are the possibilities of the multiplication of the three vectors. So the first one is a dot b into c. Here a, b and c are any vectors. So if we multiply the vectors in this form, a dot b into c, so clearly a dot b is a scalar quantity, and when we multiply a scalar with some vector, we are going to receive a vector quantity. So a dot b into c is geometrically defined and is a vector quantity. And the second one is a dot b cross c. So here you can see that we have to first b cross c, solve b cross c first, and then we are going to take the dot product of a with the resultant vector, and we will receive or generate a scalar quantity. So this is also named as scalar triple product. And the third one is a cross b cross c. Clearly we will simplify b cross c first, and then we will take the cross product of vector a with the resultant vector, and we will receive or generate a vector quantity. So these are the three possible ways of multiplying three vectors a, b and c. In two we get a vector quantity, and this one is representing a scalar quantity. Now we will talk about that what is the basic difference between these two. If both are representing a vector quantity, both obviously are representing a vector quantity, but both are the different vectors. And how these are the different vectors? Because a dot b into c is basically a vector which is collinear to the vector c. Why I am saying word collinear, not parallel? Because collinear means the two vectors are parallel or anti-parallel. So if a dot b is a positive term, the resultant vector will be in the direction of c, and if a dot b is a negative term, the resultant vector will be in opposite direction to c. So that's why we are saying that this is representing a vector which is collinear to the vector c. And if I am writing it down in this form, a into b dot c, then obviously the resultant will be collinear to the vector a. But when we talk about the product a cross b cross c, which is also named as a vector triple product, then in this case the resultant vector obviously has no parallel or anti-parallel direction with a, b or c, because the resultant of b cross c will be parallel to both of the two terms, and then the product of a and the resultant will be perpendicular to the again to both of these vectors. So it means that the resultant vector is not collinear with any one of the three vectors. That's why we are saying that both are representing two different terms, not the same terms. So here are some rules for the products we have discussed recently, that a dot b into c will not equal to a into b dot c. Clearly this will be a vector in the direction of c or collinear to c, and this will be in the vector collinear to vector a. And as far as the direction is concerned, both are representing the different directions. That's why these one cannot be the same terms. So whenever we are defining such products, the bracket plays a very important role, because it is defining that how we are multiplying the two vectors or the three vectors. Then we have the second one, that is the scalar triple product. So the scalar triple product is also named as the box product. Here is the named box product because we can write it as with the square bracket a, b and c. So we will discuss in detail about the scalar triple product. So the scalar triple product, at first we will discuss that what is it is describing, or what is the geometrical meaning of the scalar triple product. So as we discussed previously, that the magnitude of b cross c, or the magnitude of the two vectors, or the cross product of the two vectors, basically define the area of parallelogram constructed by the given vector. Similarly, the scalar triple product of the three vectors represents the volume of parallel piped having the vectors a, b and c at their edges. So we will discuss that how this define the volume of parallel piped. So here we are going to discuss about that how the scalar triple product represents the volume of parallel piped. So here you can see that this is my vector A, here is the vector B, and here is the vector C, and with the help of these vectors we are defining a parallel piped, which is basically just like a cube as we defined, like this one. but in this case the vectors are at 90 degree, but for the parallel pipe the vectors are not at 90 degree, these are acute angles basically. So now we know that volume is equal to base into height into width, so when we multiply the base and width it is equal to the area of this parallelogram, and area of this parallelogram we have discussed for the cross product that it is equal to the magnitude of the cross product of the vectors, so it will be equal to the magnitude of b into c, or the b cross c. And for height we know that we have to find out the perpendicular distance or the perpendicular length. So how we are going to define the height over here? So we have drawn a perpendicular line over here, so this is basically the y component of this vector a. And how we are defining the, so I'm not saying the y component will be the good one, because if I'm taking it to be I, j and k, or more precisely if I take it to be the two-dimensional vector, so this is my vector I in the direction of I, and this is the direction of the vector j, unit vector j, and this is my vector a with components a1 and a2. Clearly, a1 is the x component and a2 is the y component or the coordinates of this point, and I can replace a1 with a dot I and a2 with a dot j. So it means that if I'm going to find out the vector or the component of this vector in the direction of I unit vectors, and I will take the dot product with I, and if I want to find its projection on y-axis or the projection on the vector j, unit vector j, I have to take the dot product of a with the unit vector j. So similar lines, I'm going to take the dot product of this vector a in the direction of this vector n, because this perpendicular distance will be equal to the y component or the second component if this is y-axis, and for this one I'm going to take the dot product with j unit vector j. But right now it is not the ijk system, so it means that I have to take the dot product with this unit vector n. And why I'm taking the dot product with unit vector n? Because as the dot product is defined, cross product is defined, the vector n is basically in the direction perpendicular to this plane, and this perpendicular is parallel to this perpendicular height, and obviously this height is parallel to this vector in direction and have the magnitude of this, so a in dot n will be the corresponding height. So now if I multiply this unit vector n with this magnitude, this is going to be b cross c, and this is a dot b cross c. Next, we will discuss that how we can define the scalar triple product. As we discussed that if we want to solve the dot product of the two vectors, we are going to multiply the corresponding components and then add the resultants. That is, a dot b will be equal to a1 b1 plus a2 b2 plus a3 b3, and similarly, we discuss about the cross product, that if we want to find out the cross product, we have to solve a determinant within this form. So similarly, we are going to define a way in which, or we are going to define a method by which we can find out the scalar triple product. So here I'm going to check it. So for a dot b cross c means we will solve b cross c first, and then we will take the dot product of the resultant with the vector a. So for b cross c, I have to solve the determinant I, j, k, b1, b2, b3, and c1, c2, c3. So here I have expanded the one or the determinant. So it will be equal to I. So here is the determinant, the expanded form of the determinant. Then we have to take the dot product of this resultant vector with the vector a, and for dot product we have to simply multiply the components or the I vector with the unit vector I, then j with j and k with k. So this is going to be a1 b2 c3 minus b3 c2, and you can see that we have just replaced this I with a1, j with a2 and k with a3. So it means that this will be equal to the determinant with a1 a2 a3 b1 b2 b3 and c1 c2 c3. So it means whenever we have to solve the scalar triple product, we are just going to solve this determinant. That is, if we have to solve the scalar triple product, this one. So what we are going to do, we are just going to expand the determinant with the first vector with I, that is, or the with first row defining the components of the first vector 2 minus 3 and 0, because there is no the third component, or there is no component in the direction of unit vector k. Then the second vector 1 1 and minus 1, and then the components of the third vector 3 0 and minus 1, and by solving this determinant we get the answer 4. but one can attempt in this way as well, but this is obviously a lengthy one, but it's totally up to you that how you want to solve this scalar triple product. Then we have question number where we'll discuss question number 40 because it defines the basic property or very important property of the scalar triple product, that a dot b cross c is equal to b dot c cross a is equal to c dot a cross b. Here you can notice that we are following a cycle, that is a is coming or b is coming after a and c is coming after b. So a b c, here a b and c, then a b and c, and then a b and c. So we have to follow this cycle or this pattern, and the scalar triple product will represent the same terms. Why the cycle is important? Because a cross b is not equal to b cross a, so the two terms will not be the same, so we have to follow the cycle to keep it same. And how we can prove it? We know that a dot b cross c is basically equal to the determinant a1 a2 a3 b1 b2 b3 and c1 c2 c3, and we know that if whenever we change the two rows or two columns, we have to put the negative sign over here. So it means that when I'm going to interchange these two rows, I am going to place a negative sign over here, and then I am going to replace or interchange these two rows. So again, negative into negative is going to be positive, and this is representing the scalar triple product b dot c cross a. So basically we have changed the rows two times, that's why negative negative is going to be positive, and it is defining the corresponding scalar triple product. Clearly it is again the same, because we know that a dot b cross c is equal to c dot a cross b, and we also know that the dot product is always commutative, so I can replace it with a cross b dot c. So this is not as much difficult. So far we have discussed question number 37 and 38. Then question number 39, 40 and 41 related to the triple products, and now we will discuss about question number 42. Prove that a dot a cross c is equal to 0. So here we can use a result that a dot a cross c is equal to a cross a dot c, which is obviously 0 because a cross a is equal to 0. A cross a means the angle between a and a is 0 degree, and sine 0 is 0, that's why the cross product will be 0. Or you can say over here as well that a dot a cross c is equal to the first row is defining the components of vector a, then the second row is also a1 a2 a3, and the third row is c1 c2 c3. And when we take the determinant of this, and for determinant whenever the two rows or two columns are the same, the resultant will be 0. So being the two rows same, the answer will be equal to 0. Now you have to attempt question number 47, 48, 49 and 50. Now let's talk about the third type of product, that a cross b cross c, and a cross b cross c is equal to a dot c into b minus a dot b into c. So here you have to follow this pattern because of the negative sign, because if I replace the two terms or if I interchange the two terms, the answer will be in the negative one. So we have to follow the pattern that a cross b cross c is equal to a dot c first and then a dot b. And if I'm going to write down it for a cross b cross c, I will take the dot product with a first, because a is farther or at a more distance from c. So a dot c into b minus b dot c into a. So you have to keep it in mind.